Yeah, so morning. While we waiting for your friends, you can uh, fill up the attendance from Putra Blast. I think using the one that Dr. Sophie's already create. I think it's weekly. So please do so while we waiting for others. Okay, let me on. Okay. So 63. Oh, semua sekali 105. Oh, man. Okay. View. So student in this class is about 105. The latest figure is 105. Last time is in SMP they put it as 115. So the latest figure is 105. Now we at 65. So 65 are joining currently. So this Zoom account can only hold up to 100. So it's my own license, professional license, but it can only hold up to 100. So 5 people too is, maybe those under the blanket lah today. I assume those who are not joining us, maybe I can give a leeway for 5%. Those who are still under the bed sheet. Yeah, so total the full capacity for this room is up to 100. So this is a pro license Zoom, not the basic license. So time is unlimited, but we have limited participants. Okay, but don't worry. So this will be recorded, and I will upload again to Putra Blast. Attendance in Putra Blast. Okay. Just use the one that is Dr. Sophie's create up to week 14. If not, then you notify me. I will like to remind him again. Maybe just create until week 7 or week 8. If it's until week 14, so please just use Dr. Sophie's link. The Putra Blast link that's created by Dr. Sophie. Okay. Yeah. Maybe we wait for a few minutes. Okay. Hmm. Okay, so uh, good morning, assalamualaikum, and good morning. So the chapter for today, uh, is admitted or three more coming in. So we touch on Anova, one way Anova today. So for lab session, uh, we will conduct Anova lab next week. I hope there's no any more holiday, unsuspected holiday next week. So the lab session for today's we will carry out on next Tuesday. Okay. So today is a replacement for yesterday. Yesterday is Sultan's birthday. Okay. So today we touch on one factor ANOVA. One factor ANOVA. Okay. Let me share the screen first. Okay. All right. Screen sharing. Okay, screen sharing and hmm, where's the play button? Okay, all right. Can anybody see the slide? Boleh Boleh. Oh, I see. Ini macam dalam atas katil lagi bunyi ni kan. Are you still at home? Okay. All right. Okay. So today's chapter is analysis of variance or ANOVA. All right. Now, what is so the outline of today's lecture is first why you need to carry out ANOVA, and then what is multiple testing, basic principle or formula of ANOVA, types of ANOVA, which is actually you need to calculate these important parameters called F ratio, and a bit on post hoc test. Post hoc test usually follow ANOVA. If there is significant difference in ANOVA, then you proceed to do post hoc test. Okay, now this is the learning outcome. In the end of the lecture, you should able to explain what is multiple testing, define and differentiate types of ANOVA, what is F-test, and possibly this one should be done in the lab. Different type of post hoc tests and know when to apply which test. This one is better to demonstrate in the lab using SPSS. Okay, this one, the last part maybe we only touch a bit today. All right, now why ANOVA? So if you recall back last week lecture, the one that I post in a video, which only less than 20 people watch that video. I have the YouTube analytics to track my view. You ni betul-betul cuti sungguh-sungguh lah. Kan? Tak apa, siap untuk masa test sekarang. Alright. So, is this already recorded? Is this already recorded?
Recording in
Oh,
progress.
okay, now. Okay. So, if you recall last week, I put up a lecture on t-test. Okay. Now, why you do ANOVA? Because of the limitation of the t-test. Okay, now let's recall back what is t-test. I think Dr. Saufi already conduct lab work for t-test, right? Is it? Please, anybody confirm? Yes.
Yes, yes,
Okay.
doctor.
Hopefully you have conduct the online SPSS lab work with Dr. Saufi. So basically, is comparing means. Okay. Means of two groups. Okay. You compare. The limitation is t-test is you only compare the means of two groups. Okay. Okay. Sample A and sample B. That's all. Whatever the parameter is being compared, only two group at a time. And t-test can only be used with one independent sample. Maybe for example, if you are measuring, let's say, the heights of plants, the measurement is dependent variable. Let's say the height in cm. What will be the independent variable? Huh? Maybe only one, which is your treatment. Your treatment is independent variable group. Maybe the type of fertilizer, or the concentration of fertilizer. Maybe you use foliar fertilizer or compost fertilizer. One sample, one batch of sample, you put maybe 20 ppm of fertilizer. Another batch of sample, maybe 50 ppm. So meanings, you are measuring the response of one independent variable at a time. However, t-test, actually, you can have a level. In the independent variable, you still can accommodate level. Meaning maybe the type, the concentration of fertilizer is one independent variable, but uh, you can separate into two. Another two in the independent variable, which is maybe concentration and types. Uh, Fertilizer, organic, synthetic, and then 20 ppm, 50 ppm. So meaning they are level inside the independent variable. So mean Anova can expand the level of independent variable. But t-test is only one at a time. So maybe the type of fertilizer or concentration only. Now, why not use lots of t-tests, which is we call this multiple testing? Why? Let's say you have maybe sample batch A, batch A, and then you have another sample batch B, and then you have C. Okay, minimum. Yeah, minimum more than two. You can use ANOVA at least three. Three groups or more. Okay. Two samples to compare. Still t-test more than two, then you can consider ANOVA. So how many combination of t-tests that can you use or can you do? You can either compare between A and B. So one, you can compare between B and C. That's two. And you can compare, if you do t-test, individual groups, individual pair, you can have three combination, three possible combination to do t-test. Oh, lupa. Sorry, okay. Lecture slide, okay. Dah, okay. Later. Alah, lupa. Nasib baik ada ingatkan. Okay. Alright. Sometimes you can use your microphone to remind me. Sometimes because the bar, the command bar will be invisible during lecture. So I don't see the command bar, the Zoom command bar. So if anything you want to brought up, you can use your microphone. Okay, now. Okay, don't worry. Later I will upload to Putra Blast. Lupa pula pagi-pagi ni kan. Biasalah kan, very gloomy morning, right? Lecturer pun moody juga kan, based on the weather. Okay, so let's say you have a minimum of 3. Let's say to do multiple tests. Why not use t-test for each pair? So you have a combination of AB, BC, or AC. Right? Why not use? So uh, in this particular example, usually why it's not advisable to conduct pairwise tests for multiple group is due to what we call you are inflating your error. Yeah, you will be uh, inflating in this case type 1 error. Type 1 error. Okay, the more you do comparison, pairwise comparison between many groups, let's say A to B, B to C, C to A, C to D, A to D, something like that. If you add, let's say more group, more group to the mix, right? You are adding more elements. So by doing so, you'll be inflating type 1 error. Now, type 1 error is, you have heard this before. You have come across this before. So the other name for type 1 error is alpha. Yes, that alpha which is at 0.05 or 0.01 is the same thing. So this is another name for alpha. It's the same thing. So alpha is actually representing type 1 error. Okay. So type 1 and type 2 error, they actually two types of error in stats. So when you perform a statistical test, usually you will take one sample. You take one sample from a population, right? One small element from a bigger population, but from that sample, you hope to do inferential statistic. From that sample that you took, you try to ascertain, or you try to uh, put some pictures, put some, you want to translate what is happening for the whole population just by that sample, because you don't have the means to sample all the whole population. Resource wise, time wise, maybe not possible. So from that one sample, you want to have a bigger picture. So you have to think about your sample, the one that you took. You have to think about your sample in the context of all the potential sample that you have collected. Okay. This is representative. This sample is representative of the population. So you want to take the correct sample. Now, your sample might have type 1 error, also called alpha. It is the likelihood that you incorrectly reject the null hypothesis. Okay, we will explain a bit later what is type 1 and type 2 error. And this is just definition first. Type 2 error is called beta. Okay, so this may be the first time you heard of beta. Alpha, from the beginning of hypothesis testing, you already know, accustomed to what is alpha. Now, this is called beta. Beta is the likelihood that you fail to detect the effect that that your alternative hypothesis is trying to uncover. Okay, it's better to explain by using this table, this box. Okay, so this is, I put it as overview. Now, okay, so this column and this row, pay attention. Now, this is your study. Your study, your experimentation, and your measurement. Maybe sometimes it's better to say that what you measure. What you measure. Okay. Maybe you measure the soil sample, or you do survey on the population of UPM student. So this is your findings. And from your findings, you try to, from your test statistics, you try to decide and put some conclusion. And this is the state of the world, which is the truth. what actually really happened is representing by this box, and this is actually what you find, what you measure, your decision. Your decision is based on sample. This one is the population, the real, what happened, what really happened to the population. Now, okay, so we go one by one. Okay, now we go to the first blue box at the top. This one, okay, the left top box, the blue box. Okay, now let's say if null hypothesis. First thing is, what you know, what is your null hypothesis? Your null hypothesis is the status quo. Uh, the status quo, the uh, the existing condition. Okay. Here maybe you do some intervention. Intervention. You do some intervention. Mean you do something. You experimenting to the world, to the environment, which is represented by the truth. Okay. You do some intervention. You do some experiment. Maybe to the soil, to the groups or whatever, and then you administer your measurement. So when you say that, when you measure something and then you say, I think, uh, hash alternative here is the research, the research hypothesis. What is your researching? Okay, and this one is status quo, usually the normal condition, which is if you do anything to the world, nothing changes. Okay, status quo mean nothing changes. Whatever intervention, whatever treatment you do to the world, to the environment surrounding you, nothing changes. But if anything, any effect changes, mean what? You try to promote your alternative hypothesis. Now, let's say you measure and then there is effect actually present. Right, okay. So look at this box, the first box. You do some intervention, measure, and then you measure, and then your measurement device or your survey say, oh, I think something happened actually to the world. So there's an effect present. And indeed, the truth say, yes, the effect does present. eh, Due to your treatment, the effect does present. So what? So what is the most common thing to do? Logical thing. So you reject the null hypothesis, right? Because some effect happen. Meaning the null hypothesis here is false. So you can now promote your alternative hypothesis. Now, okay, go down to the red box below, which is type 1 error. Type 1 error is what we call as false alarm or false positive. Meaning what? You do intervention, you do survey, and you claim that there is something happening, some effect happen, but in truth, nothing actually changes. And the world, the truth say nothing happened. Actually, it's just measurement error. And it give you positive result. In fact, it's not positive result, nothing happened. So you call this type 1 error. Type 1 error. Okay, straight away, you remember type 1 error is symbolized by alpha. Okay. Now, type 2 error. Okay. Top box at your right. At the top, the red box at your right. Okay. Type 2 error is symbolized by beta. Okay. So meaning what? Your intervention that you conducted, that you impose on the environment, and then you measure the said intervention, you didn't detect anything. In fact, but however, the truth is on the contrary. Otherwise, some effect do happen, but you fail to detect. Okay, this is what we call missed opportunity. you have the missed opportunity to detect any effect present to the treatment. So that's why I put it here in the bracket miss, or false negative. Your measurement yield negative result, but in fact there is actually some effect present. So we call this type 2 error. Now the last blue box at the bottom is okay. You do intervention, you proceed to do measurement, you didn't detect any changes or any effect. And the world also agrees with you. Meaning what? You fail to reject your null hypothesis. The world stays the same. You administer some treatment, but the world stays the same. So you retain the null hypothesis. Okay. In mathematics, so the blue box at the bottom is, we call this as 1 minus alpha. 1 minus alpha. The blue box at the top is 1 minus beta. Okay. The mirror image of their red box. Alright. Okay. Now, okay. This is the, I can say, the common textbook example of the box that I've explained earlier. Usually, the textbook always present pregnancy test kit case. Okay. Now, okay. Let's say there are 4 things that can happen when you take pregnancy test. Okay. Now, your measurement device can be accurate. Let's say you are a girl. Okay. A girl going to the clinic. Going to the gynecologist. Maybe. And then you want to perform a pregnancy test. Okay, now the test method can be accurate. Okay, and says that, okay, listen, you are pregnant when you are actually are. So what will be the symbol here? Number 1, you are pregnant when you actually are. Okay, in this case, okay, first, we establish the null hypothesis for pregnancy situation. What will be the null hypothesis here? Null hypothesis here. Where should I write here? Maybe at the bottom lah. Maybe okay. Null hypothesis is the status quo, the normal condition. Now, maybe just to not let you doze off, I will ask some of you. Let's say you follow or not my lecture. Just a way of taking attendance and also just to know whether you follow. Sachini Ilangovan. Are you present today, Sachini? Nor Afrina. Sachini. Is there a Sachini today? Sachini. Yeah, I'm stop sharing first. Okay. Maybe I should look at the okay, look at the names that are here, that are present. Who can I ask? There's a lot of you. 100, 100 and 105. Mm, where? Adeline. Okay, Adeline. Ada kat sini. What's the name of Adeline? Okay, Adeline. Okay, I can see your name, Adeline. Okay. So I hope you don't doze off yet. Okay, okay, I share again the screen. Adeline, are you here? Adeline? I just want to ask. Okay, simple question. Adeline. Kalau tak ada maksudnya saka tu kan. Kan? You just only present in names but in spirit but not in physical form. Okay, Adeline, going once. Adeline. Sekejap. Okay. Adeline, going twice. 3 times. So it means you are not present. Okay, simple, Okay, Okay, you just present in spirit, yeah, not in physical, Okay, Adriana Shakira. It's very easy, if you record but not in attendance, so I just override your attendance. Adriana Shakira, are you here?
Yes, doctor.
Okey, ada nasib baik, Kalau nama saja tapi tak menyahut, maksudnya tak adalah sebenarnya. Okey, number 1. Okey, number 1. The test can be accurate and says that, your test kit is accurate and says that number 1. You are pregnant when you are actually are. Okay, now the first one, null hypothesis. What is the null hypothesis here? Okay, what is the null hypothesis here?
I will just try because I'm not really sure.
You're not really sure? Okay.
I think
Okay.
all males will get the alpha.
No, we are talking about null hypothesis first. Okay,
Uh,
What is the null hypothesis here actually? What is the null hypothesis statement here? The status quo. Okay, what is normal condition for girl? Okay. Okay, this is pregnancy situation. Normally, we girl pregnant or not pregnant? Normal situation.
yes. Yes.
Apa dia?
Yes, women will pregnant.
Nah, normal condition, women or girl, normal condition on any day, are they pregnant or not? Normal condition, normal situation every day. You wake up, go to lecture, you come back.
No.
No, okay, So, it's not normal for a girl to get pregnant, So, no pregnancy, Okay, in normal situation, girls won't get pregnant, right? You do your normal stuff, you go to lecture, you go to cafeteria, right? You won't get pregnant, right? But if you administer some treatment, okay, get pregnant. So the alternative hypothesis here is girl get pregnant because there are some intervention, there are some treatment happening, some experimentation. What is that experimentation? Is the one that you did your extracurricular at night time, during bedtime with your spouse, right? Yang patah katil pun ada kan? Okay, so that is not normal, So, you only get pregnant due to some experimentation, due to some treatment going on privately at night, something like that. Okay, Now, so, now you are feeling something in your tummy, let's say, married with a spouse, proceed to do ahem, okay, go to the hospital. Now, okay, the doctor administer, okay, so you have 4 situation, 4 possible situation. Now, the test can be accurate and says that you are pregnant when you are actually are. So, what is the symbol there? Out of 4 symbol, what is the symbol for number 1? Muhammad Razik Irfan. Muhammad Razik Irfan. Muhammad Razik Irfan 3 times mean you are not here actually, Okay, very simple, Nur Alia Narzilan. Okay, this one is from bioprocess. Adakah Nur Alia? You.
Yes, doctor.
Okay. Situation number 1, what will be the symbol? Alpha ke, beta ke, 1 minus alpha ke, 1 minus beta? Which one?
Alpha.
Alpha? Alpha is what?
Like 1 error?
Type 1 error is what?
Not sure.
Tadi je. Baru je tadi slide lepas. Type 1 error is, the other word for type 1 error is? False alarm. Is this false alarm? Number 1, is this false alarm? You are pregnant when you are actually are. Is this false alarm?
Oh, no.
No, this is what? This is what? Okay, this is represented by what? What symbol? So, instead of alpha, this is 1 minus beta,
Oh.
which is the truth. Okay, you do something to the girl got pregnant, the test kit says so. Okay, so you reject your null hypothesis. Okay, now number 2, you are actually not pregnant, maybe just a tummy ache. You are not pregnant when you are actually aren't pregnant. And the test kit is accurate. So meaning what? Number 2 represent by what? Number 2? Number 2 represent by what? T Fong Ying. T Fong Ying. Ada ke?
Yes, doctor.
Okay, number 2. What will be the symbol here? Represent by what? Okay.
1 minus alpha.
1 minus alpha. Correct. It's 1 minus alpha. 1 minus alpha. Okay. You are not pregnant. The test say you are not pregnant and you are not really pregnant, meaning what? You retain the null hypothesis, which is 1 minus alpha. Okay, so and then, so the 3 and the 4, it can be inaccurate. Your test kit can be inaccurate and says that, okay, number 3, okay, don't need to answer to ask until number 4. If you get number 3, then you know what is number 4. You are pregnant. So the test kit can be inaccurate and says that, what the result say, you are pregnant when you are not, which is a false alarm. Of course, when I say false alarm, which is, that will be false positive. False positive meaning what? This is alpha. Okay. And then number 4 should be beta. Okay. You are not pregnant when you are actually are. A failure to detect the effect. Okay. All right. Okay. All right. Now, this is error in significant testing. So this is usually the typical textbook example. Significant testing is the other word of saying hypothesis testing. Okay. It's the same thing. Significant testing is mostly used for people in chemistry. They are more fond to say significant testing. In people in chemistry. So errors can happen. So a type 1 error is rejecting a true noun, meaning false positive. If you look at this old man, bedridden old man, and there's a young guy, young doctor came and then do some diagnostic and say, you are pregnant. Congratulations. Pening orang tua tu kan. What? Right. How to tell my wife? Something like that. Okay, that's first situation. Another situation is type 2 error. You are 8 months pregnant. Besar je, boyut je kan. Go and meet the doctor, but the doctor administer a test kit. Still say, you are not pregnant. You just maybe have a beer belly, something like that. Kan? Sedih je makcik tu. Right. Okay, now. Okay, so the pregnancy test. The pregnancy test says that this example exemplify let's say if type 2 error is the probability that a statistical test performed on this particular sample failed to detect the effect, which is the pregnancy. Then what is the probability that the test using this sample will successfully detect the effect? Okay, it's just a word play there. So beta is, let's say beta. Beta is the likelihood of that test kit fail to detect the actual result. Okay. This is just a word play. So type 2 error is beta. So let's say if we put a value of a probability of a certain test kit, a certain measurement will fail to detect a certain effect. So let's say we put 0.2, right? So the other word of saying that statement is what will be the success rate, what will be the probability of your test, your statistic test to actually detect the effect, the actual effect. So meaning what? Probability of failing to detect effect is 0.2. So meaning probability of successfully detecting the actual effect should be 0.80 or 80%. Now, 80% here means, so 1 minus beta has a special name. The probability of successfully detecting the effect present, 1 minus beta, it has a different what we call terminology, which is called power. How powerful is your test statistic? How powerful is your test? So if the likelihood of failing to detect 20% mean the likelihood of success should be 80%. So this is representing the power of your statistical analysis. 80% chances to detect the effect. So what is the definition of power, which is 1 minus beta? The ability of a stat test to detect a relationship or difference. Okay, the word different here will carry a meaning. Detect a relationship a bit vague, but to detect a difference, yeah, there's a mathematical meaning to it. Or the other word of saying, the probability of rejecting null hypothesis when it is false, which is a good thing. So therefore, it should be rejected. So it's a good thing if you can reject null hypothesis when it's proven to be false. Okay, now the concept of power, just a bit. So power is, if you put it in a word, power is probability of rejecting null hypothesis given that when it is false. Okay, which is the other way of saying is 1 minus the probability of not rejecting null hypothesis, failing to reject, even though null hypothesis is false, which is the whole sentence is actually beta. Probability of not rejecting null hypothesis when indeed your null hypothesis is proven false. So the whole sentence here in the bracket is referencing to beta. So 1 minus beta is we call power, which is the probability of not making type 2 error. Okay, that's how plainly to say what is beta. Now, just to put into perspective, let's say we let's assume a distribution. Let's assume a distribution, where you have a null hypothesis that say mu1 is equal to the population mu. So this mu1 is equal to, can represent the population mu. This is your first hypothesis. So always start with assuming your null hypothesis is true. Okay, in statistical test, the existing condition is always true, but your challenge hypothesis is actually you try to challenge your null hypothesis. You want to prove your null hypothesis to be otherwise. Okay, something else. So in classic way, in statistical classic way, they say this is similar to court cases. Similar to court cases, which are the defendant assume guilty until proven otherwise. Assume innocent, assume guilty pula dah. Kalau guilty tak payah nak masuk court kan. Sumbat terus dalam jail kan. Okay, in any cases, the defendant is assumed innocent until proven otherwise. Okay, that's the first thing in just like insignificant test. So assume first that H null is the truth. Okay, and then you proceed to maybe disprove or whatever. Now, assume that maybe mu1 is your can represent your population mu, and then you did something, some intervention, some survey, whatever. Now, this is your what the survey says. Your what? The result. The result. Okay, okay, the result. Okay, now you can say that the H null is false. This is what you get. Mu, the new mu is equals to mu2. Now, mu2 is different from different population because why? the average mu already exceed the alpha. So this is your critical. So this, let's say, this is your T critical. So your T critical, assuming if this is a T test, your mu is already past T critical in such a way that it creates another distribution, a new distribution altogether. It's not overlap with the old one. So it's so far off that it creates a new distribution. So meaning what? It's not from the same population. Okay. So you can say that now your H alternative is, you try to prove your H alternative is mu is no longer equals to mu1 because your mu2 is so far off from the actual mu, from the mu1. Okay. Now, how much the difference, let's say from, if you, let's say, take the average from mu1 to mu2. So the differences is what we call effect size, represented by D. By D. Okay. So if you want to know where lies the alpha, so alpha you already know, is at the tail end, of the original population, original distribution. For beta is usually is this tail end. This tail end. When you already done your survey or your experiment, you create a new distribution. So this tail end, the one that overlap with the old distribution, is called beta. The likelihood of not detecting the effect. All right. Now, effect size is the size of difference between your null and your alternative hypothesis that you hope to detect. D here. So, D can be categorized as restroom. Okay. Okay, iyalah tu. Okay, nanti I put here restroom. Okay, restroom. Nanti kena tanya balik lah. Alright, now. Okay, now effect size can be categorized as small. Effect size D, represented by the character D, can be said to be small, medium, large, and maybe huge or something like that. So effect size determines the strength of a relationship or difference between variable. So we can say if too close of a D, maybe 0.2, we can say that effect is very weak. Like the first one, like the first distribution here. The D, the differences between, the red distribution is the original, your null condition. The blue distribution is your new distribution, the one that you measure. Okay, if it's just move slightly a bit, with the size of 0.2 difference, you can say that there is small effect, actually small effect happening in your treatment, in your experiment. Okay, 0.5 you can say medium. You can say that maybe these two distributions still overlap, meaning what, both are still considered to be the same population. 0.8 a bit larger the effect, but maybe still from the same population. Let's see if the effect is 2, the distance differences, 19% overlap. 19% overlap is here. Okay, so you might say that there is a large differences between the null condition and your experimental condition. So unlike p-value, which is a number that is given, the p-value is like, okay, you put 0.05, 0.01, something like that. Effect can be used quantitatively to compare results of different studies. So let's say, maybe you do a t-test, and then between two distribution or between two sample, and then you came up with a p-value of 0.03, assuming which is less than 0.05. Okay, now you can say that I think there is significant difference between the two sample. You might use that to conclude. Okay, you put it in the return. You can say that P is less than 0.05. So meaning what? There are significant differences between these two groups. However, how large is the differences, the magnitude of differences, you don't know. You can only know by uncover D, the effect size. Okay, so mean effect size can be used to compare actually, to compare how large the differences. P size is just to say, difference, is there any significant or non-significant? But D shows you how much the difference is actually. Okay, for example, this is just for example. Let's say you compare heights between 11 and 12-year-old kid. It may show that due to the maybe biological condition, maybe growth spurt, 12-year-old, you can say biologically significantly taller than 11. But it is difficult to visually see a difference. Meaning what? Okay, you just have a difference of 1 year, you will grow slightly taller, right, between 12 and 11. So you can say that effect is small. So if you look from afar, these two groups of people, 111, 112, maybe you can say, I think that 12-year-old is taller, but ever so slightly. Okay. However, a significant difference in height between 11 and 18 years old kid. A bunch of 11 kids, 11 years old kid, and then mingle with 18-year-old kids, then you can see the height will be obvious. So you can say large effect size. Okay, now value of effect and interpretation. Okay, so let's say if you do a test between means parametrics, between means parametric. So usually between means, okay, like the t-test. So the D is called Cohen's D. Maybe this is t-test. So the D is Cohen's D for parametric, or sometimes people use HG. I seldom see HG, but I always see Cohen's D. So if your Cohen's D calculated by computer is less than 0.2, you can say the effect is trivial, not so much. But the Cohen D is registered as 0.2, small, medium, 0.5, anywhere higher than 0.8 is large. So meaning if you do treatment to a certain group, you get Cohen's D of 0.8, mean there is actually large differences between two samples. Non-parametric, all this while you are learning parametric test. Non-parametric, maybe 2 weeks more. You will know what is non-parametric. All this while, you do measurement, right? You do measurement. So anything that can be measured is parametric. Anything that is measurable represented by continuous factor, a continuous data type. Let's say pH, right? pH is continuous. It's not discrete. pH you have, let's say 5, 5.1, 5.2. So you have a continuous scale. And then your data follows normal distribution. Usually you can call this parametric. You can use a parametric test. Non-parametric, the one test that defies the data is not normally distributed, and usually the scale is not continuous. This is a plain way of saying. Non-parametric usually falls under that category. So for you to use, let's say, a t-test, an equivalent t-test for non-parametric data, so you have a rank by serial, rank by serial. So work as the same as Cohen with the same value, less than 0.1 trivial, all the way to 0.5, more than 0.5 large. Okay, correlation. For correlation, you will learn later what is correlation, correlation and regression. So this one is parametric. Correlation is identified by the coefficient. You call this Pearson coefficient. So that's the name. I'm missing the name here. Pearson's correlation. So given by the R, so less than 0.1 trivial, all the way to 0.5 large. This one is parametric. Non-parametric counterpart is Spearman rho and Kendall tau. And then there's a multiple regression. Multiple regression is something like this. Y equals to maybe x1 A plus B x2 plus C x3, so on and so forth. So let's say your response, you have one response, but depend on many factors, many input factors. So that's multiple correlation coefficient. So represented by R, Okay, so trivial, less than 0.1. Large effect is somewhere around more than 0.5. Okay. Okay, now, so by if the distribution moves so far away from the normal null condition, you can say if the effect size is so far, so what it implies, meaning if the distribution goes so far away, mean you get lesser area for beta. Meaning by getting lesser area of beta, of course, the area of 1 minus beta will be very huge. Very huge. Meaning what? The larger the effect size, the larger the D, contributes to the larger the power of your significant test. You have more likelihood to detect the event, the truth. And the smaller the probability of making type 2 error. Okay, meaning from the area, beta is getting lesser and lesser. Okay, if you have bigger effect size. Okay, consequence of pregnancy test error. Okay, let's say if you got diagnosed with type 1 error, the test will raise a false alarm. Okay, depending. Either you get very worried or excited. Right, false alarm. Okay, Okay, so you may already run to the store to buy baby supplies if you are expecting a baby, but actually you are not. Right. So what happened? So you incur unnecessary cost. Buy so many diapers, buy so many, baby. You buy baby cribs, but 9 months down the road, nothing came out. Right. Came in. You may spend days or week panicking until you realize that actually is the test kit fault. Okay. If you are diagnosed with type 1 error. Okay. So there are some repercussion. So consequences. Type 2 error. Type 2 error. The test fail detect your pregnancy. You are carrying a baby inside, but the test kit is faulty. So you are thinking, maybe what? It's just due to the what? Due to overeating or something. Right? Or maybe because you say, I'm not pregnant yet, so I don't have to stop drinking or smoking or eating, right? And may potentially harm the fetus inside. So maybe you aware too late. Maybe aware too late that actually you have a baby inside. You didn't seek prenatal medication attention. So in the case like this, a test designer need to think on how to minimize both type 1 and type 2 error. Because faulty measurement may lead to psychological and cost ramification if either kinds happen. So we always try to minimize type 1 and type 2 error, which comes to multiple testing. Now, definition of multiple testing is why we don't do t-tests pairwise for many, many groups. And why we opt for Anova. Okay, we have until 11, right? I think today, right? I think our class end at 11, so 30 minutes more. Okay, so multiple testing usually have if you let's say do pairwise t-test for multiple group, you have the potential to increase type 1 error if you do repeatedly. Okay, so when conducting t-tests, default is we assume 5% chance. Your p-value, your alpha is at 0.05. So that signifies 5% chances that we might accept an experimental error effect that is not real, which is type 1 error. Okay, But if you do so many series of t-tests, on the same data set, this error adds up. Okay, so we call this inflation of type 1 error rate. How this is happening? Okay, how this is happening? Okay, let's say we compare A, B, C. Three means A, B, C. So you have a combination of A and B, B and C, and A and C. Okay, all have their own alpha of 0.05, 0.05, 0.05. Okay, each of them has their own alpha set value. Okay, so if you assume that each test is independent, overall probability of the number of type 1 error for 3 tests, sorry, probability of no type 1 error, which is 1 minus alpha, meaning what? For, let's say, every test you set alpha at 0.05, so meaning probability of not committing type 1 error should be 0.95. Okay, the other way of saying it. Now, so probably what happened is your alpha value, if you do 3 times, 3 combination of tests, mean what happened? Alpha minus 1 over 0.89 to the power of 3. So 1 minus, so 0.95 to the power of 3 will become 0.857. So you end up with cos 0.143. Or instead of 5%, your alpha is inflated to 14.3. Okay, which is more than acceptable value of 5%. Okay, meaning if you do, let's say, a comparison between A and B, and then B and C, and then A and C, actually your alpha value getting more and more and more. Okay, so it's not wise to do like this. So error rate across stat tests conducted on the same data is known as family-wise error rate. Family-wise error rate, depending on the number of tests that you've done. Okay, so we want to avoid that. We want to have increase in alpha. Mean what? Increase in alpha mean increase in positive. False positive. We don't want that. Okay, so because of this, we need to carry out alternative tests that actually look on the overall experiment of many groups, but you only use one single test to solve this. Okay, now it tests the null hypothesis that in a set of data there is no significant difference at all. So Anova is one example to counter this. So you establish a null condition. Let's say, so so we also looking at the mean, at the average value of every group. Yeah, so your null hypothesis is written like this. Mu1 equals to mu2 equals to mu3, maybe equals to mu4. How many groups that you have in your treatment? How many treatment until maybe mu k. So k is the number of treatment or the number of groups that you consider. Okay, so this is the null condition. So set beforehand that the means, the average of each group is the same, non-significant different. Okay, this is how Anova works. So alternatively, the H, if you want to know, if you want to challenge, so simply at least one mu from each group, from one of the group is different than the rest. This is all Anova is all about. That's all. It's just want to prove that at least one mu from whichever treatment, whichever group, at least one is significant different. This is all Anova. Dah boleh tutup buku. Okay. Now, you have several type of Anova. The most common one is one-way independent Anova. Okay, one-way example. One independent group, let's say H. This is just one example. one independent group, let's say 10 years old kids, and then you measure the height, just like previous example. 10-year-old or 11-year-old, some bunch of 11-year-old you put in a group, you compare with 12-year-old. So the height is dependent, measurable, and then the age is the independent. Okay. So let's say you have 4 groups, 10, 11, 12, 18, something like that. You compare. Is there any significant difference between them? Okay, that's one example. Two-way independent, maybe you have two independent variable, two independent, and still single dependent, which is still a height. In this case, maybe you have a group of people, 11-year-old, but there's a girl, there's a boy. Another group of 12-year-old, but split into boys and girls. So in this case, you have two independent variable, but still one measurable variable, one dependent, which is the height. Okay, this is two-way. All right. One-way repeated ANOVA is only one independent variable. Okay, maybe exercise type, maybe jogging. One independent variable is jogging, jogging or running. Okay, and then you measure the blood participant of the runner, the blood pressure. Okay, so blood pressure depends on the type of exercise, maybe jogging or running or marathon, something like that. And the same sample set, the same participant, will be tested in all conditions. Okay, maybe light brisk walk. Let's say the type of treatment is first exercise, brisk walk. Yeah, you measure the blood pressure, and then you measure again. Another 1 hour, you measure again. Or let's say marathon. The start of marathon, you measure. Maybe halfway, you measure. Maybe near to the end, of the marathon, you measure again. So you repeatedly measure the same variable. But still, it's running. The exercise type is running, but you measure repeatedly. All right. Now, basic of ANOVA, compare the means of 3 or more. So 3 or more, 3 plus plus. Okay, minimum you need 3. If you have 2, still you test. So need to first test the null H that all groups means are equal. So like I've created the null H. You want to test whether M1 equals to M2, so on until mu K. K is the number of groups. Okay. Different if any one of them is different. The null hypothesis, if the null is rejected, this means that group the means of the group are not equal. Possible can be that mu1 not equal to mu2, not equal to mu3, so on and so forth. Okay, or mean A and B is significant, is different, is the same, but C is significantly different. Maybe mu1 equal to mu2, but not equal to mu3, something like that. Okay, it's either way. You get the idea. Okay, basic principles of ANOVA. Okay, you calculate how much variability there is between scores, which is can be, we call it as a total sum of square. Okay, so you have a ratio. You have a ratio. So we have a ratio of between groups, variability between groups, which is we call systematic variance. This will create, if in the ratio, this will create the numerator, the upper part of the ratio. And there's another one within groups, the variability within group, which shows how much variability due to individual differences. This one will be the denominator, the bottom part of the ratio. Okay, so you compare the amount of variability explained by the experiment to the amount of variability due to unknown factors or individual difference. So these two factors will become what we call F ratio. Okay, F ratio. So ANOVA is basically comparing F ratio. to the F table. So F ratio is variability between groups or variance between group. So this one usually mean square between treatment. So that's, and then this one we doing group is mean square error. So in the software, usually the top one is called mean square. Mean square treatment. Treatment. This one is mean square error. Okay. Now, the larger the ratio between groups, variance to within groups, mean the larger the numerator, mean less likely the null H is true. Meaning what? The larger the top part means distribution is not from the same population. Distribution may be group A to group B or group A to group C. One of them has a different distribution. Okay. So, but if the F ratio is, meaning F ratio is significant. Okay. So we can conclude that there is differences in the group means. So Anova is basically just to test whether one of them, at least one of them, has a mean different than the rest. That's all. Okay. So if your numerator is very high, you have higher value of numerator MST than MSE, you can say that independent variable has an effect on the dependent variable. Okay. All right. Now this is working example. Just to show you how they calculate Anova. But you don't need to remember. Just an appreciation. You don't need to remember the formula. So this is work example. Researcher would like to test association of hormone, gibberellin hormone, the administration of synthetic gibberellin and the plant growth. How tall the plant grow. So gibberellin administered at 3 different concentration, tested on 21 different plants, mean each sample has 7 specimen. The height of each plant was measured. So this is the raw data. Okay, now how to calculate ANOVA? Okay, first step, find the grand mean. Oh, the X double bar. Okay, how to find the grand mean? The grandest of all mean what? It means that the average of all these 21 data set. So maybe you sum for 0 ppm, 184, 250, 490, 489. You came up with 923 summation, and then divide by 21 data set, you will get 43.98. The grand means the mean of sample means. So many means in a sentence. Now, second, find the sum of square between treatments or groups. Meaning, okay, you have the grand means. Now you need to subtract. You need to find the mean of each group. Meaning this is group 1, group 2, group 3. Okay. So this is called sum square between treatment. Okay. And here is the sample size of the ith population acting as a weighing factor to the sum square between treatment. So I here is 7, which is this number. 1 to 7 specimen. So this is the X bar. X bar for group 1, 26.29. X bar for group 2, 35.71. For group 3, 69.86. So you put everything in this formula. Yeah. So this is a baseline. So grand mean act as a baseline to compare each groups. So this is I highlight in different color. So you will get SST as such this value, and then you calculate the mean, the average. So you get sum square, then you need to calculate mean square. Mean square between treatment is SST, which is 7,357.24 divided by the degree of freedom. So K is the number of group. You have 3K here. K equals to 3 because K is number of group. Sorry for the handwriting. So K minus 1. Degree of freedom is always minus 1. So divide by 2. So you got MST, the top part of your ratio, F ratio. All right. The fourth, calculate the bottom portion. First, find the sum square error. Meaning how? X bar Kj. X bar mean X bar K is this value. This value. Okay. So plus X bar 2. This one J. J is like here. J is like sorry. So let's say this one is X11. X12. So Xi is the number of placement, and 2 here is the number of sample. So this one is X13, X14. In this case, for 25 ppm, this one will be X21, X22, X23, so on until X27. This one is X31 until all the way to X37. Okay. All right. So this is how you calculate. First, you calculate the X1, X2, X3, the group. Okay. So this becomes your formula. So let's say for X11 is 17 minus the 26.29. Okay. And then you proceed for every cell. So by using this formula, you will come up with some square error, which is 223.43 plus 351 plus 2952. Okay. Sum up, you got 3,527. And then what is the mean? The mean square error, MSE. So MSE is you divide by, you have number of group, which is 3. K equals to 3. And number of your specimen. Specimen is 1 to 7. So you have the K is 3. The number of samples or specimen in the group is 7. So you divide by 18. Right. So here is 3. Sorry. Okay. Wait. Okay. Yeah. So this one is 352771 divided by 18. So there you get this value. And then to know if there is a significant difference, you calculate the F ratio. The F ratio is MST divided by MSE. This is the portion of MST. This is the portion of MSE. So what is the value? You calculate. So this F ratio is significant to formula to calculate variance. The normal variance. Okay. So you get F of 18.77. Okay. So you don't need to what I say here. Sekejap. Okay. I need to stop sharing. Stop sharing from iPad. Ada orang terkeluar? Admitted. Sorry. Okay. Sorry. Okay. I just want to share my Excel. My Excel of the same example. So before we close for today. So before we stop. All right. I just want to share screen. My screen. Okay. My screen. Okay. Okay. Of the same result, the same data set, gibberellin and plant height. Okay. How to calculate? Now, so if you follow my recorded lecture last week, you should already know that in Excel, you can actually do Anova. How to do Anova is go to data, Yeah, go to data, and then go all the way to the right side of the ribbon. This top part we call ribbon. Click on data analysis. Okay. And find, in this case, Anova single factor, because your independent factor is gibberellin concentration. You measure plant height. So Anova single factor, click. Okay. Now, for those who don't have data analysis, in their Excel, let's say when you click on your Excel, this thing is missing. Afraid not, actually is hidden, hidden in plain sight actually. So what you can do is, actually for people in bioprocess, I already teach this, how to access. For people in biochemistry, student in biochemistry, so if you first time finding where to get data analysis step, so go to file, uh, provided you are using Microsoft 365, Office 365. So go to all the way in the file, all the way to option. At the bottom, click on the option, and then you have Excel option. Excel option, go to add-ins. Go to add-ins. Okay. So I have here active application add-ins. So I have activate my data analysis analysis tool pack. But those who don't yet activating their add-ins, so your analysis tool pack will be somewhere here, inactive application. How to activate? Go to the bottom, manage Excel add-in, click go. There is an add-ins option box. Tick, just click on the analysis toolbox. So I've already installed, so that's why I have a tick mark here. So I've installed two from this add-in. One is analysis toolbox, another is solver add-in. Because I'm teaching modeling for bioprocess student, so I'm using two things here. One is analysis toolbox, toolpacks, and another one is solver add-in. So after you tick, just click OK. So for me, I just click cancel. For you to add, you just follow these steps. Now, how to do Anova? Again, go to data analysis. If you already installed the add-in, go to data analysis. Choose Anova single factor. Click OK. You have this window option. And then, let's see, input range. Just click and then drag from the top to the bottom. Okay, to the bottom. Okay, and group by, the group is what? Symbolized by column. So you arrange your group by column. 0 ppm, 35, 50 ppm is separated by column. Click on this, this click mark, this box. Click on it because the first row is your title. The label actually is the first row. So click on it. Alpha set at 0.05. And then output range, okay, maybe somewhere next to the table, your output. So click enter. Okay, so you have generate your Anova table. Okay, previously I just explained to you the formula behind Anova, the formula behind Anova, how to calculate, but no need to go all the way to remember all the formula. You just do what I told you, and you get this Anova table single factor. So this is descriptive statistic. Summarizing. There are three groups. Number of specimen in a group, 7. This is the sum, average, variance. So this is descriptive part. The inferential part, the Anova is here. Okay. So MST is between group. MSE is within group. This is mean square. Mean square. So this is MST. This is MSE. Used to create the F ratio. The F ratio here calculated as 18.77. Now, what you need to compare? You need to compare with the F table or F critical. So this value is compared against this value. Okay. Now, so F ratio, the F statistic here is bigger than F critical. F critical is the F that correspond to the P value of 0.05. Okay. So two ways of interpreting. If F statistic is bigger than F critical, meaning what? Of course, there are significant difference within in this group. There are significant differences. Okay. Other way of looking is if you look at p value, the p value is 0.000394. That's 3944. You compare against which is so much less than 0.05, which is your alpha, your threshold alpha. So anything that is lesser than alpha, so meaning what? Meaning there is significant differences. Example, if you remember, in hypothesis testing, the one that I lecture, anything very low, then there is normally means what? Something happening to your system. Mean what you did to the system, the intervention is happening. Bear some fruits, bear some result. So p value so low, very low than 0.05, then there is significant differences in the groups between 0, 25, and 50 ppm. Okay. But Excel has limitation. It cannot do post hoc test. Okay. In post hoc test, you have to rely on SPSS. All right. So okay. Last before we finish. Okay, post hoc test. Okay, post hoc test. Yeah. Okay, post hoc test. Why we do post hoc test? We want to do some subset, some clustering. Okay, yes. All people, most people usually will go for this. After you have established that your ANOVA tells you that the group means are significantly different. Okay. If there is significant difference between the group means, that's how ANOVA tells you. Only there is differences. Which group difference? Is not within the capacity of ANOVA. It's just say that ANOVA say there is differences, significant differences. Which group is different? That you have to resort to post hoc test. So need to conduct post hoc test to compare the group pairwise again. This time you are allowed to do pairwise, even though you have multiple group, more than 3. At this moment, you can do compare group A to B, B to C, C to A. This one is permissible, but by using post hoc analysis. Why it is possible? Because it's calculated in such a way that it won't inflate your type 1 error. So type 1 error is not inflate like family-wise error rate. Instead, it's been controlled at 5% all the time, even though you do pairwise testing for multiple groups. How to do? Let's say there is a method. Example, there are many post hoc tests out there actually. If you do research work, maybe for your final year project, when comes the day that you need to do analysis, stats analysis, for your test, for your sample, and if you do multiple, if you do many treatment of the sample, and you need to compare which treatment is the best among your sample, maybe you have to resort to post hoc test. After only you establish that ANOVA is significant. So one of them is Bonferroni. So Bonferroni divide the alpha by the number of tests that you have conducted. So if conduct 2 tests, instead of alpha 0.05, you just divide. It's become 0.025. So significant difference need to use a p-value of less than 0.025 instead of 0.05. Okay, that's if you choose Bonferroni post hoc test. Okay, so many post hoc tests. One is multiple comparison. Okay, means what? You compare means of each group with the remaining group, see if there is significant difference. This is the most that we use. The normal type of post hoc that we use. You come across. This is the most popular. Tukey, highly significant difference. LSD is least significant difference, and Bonferroni. Okay. Usually this is the default. Tukey is like the default that people choose. Yeah, if you compare between groups. Yeah. And then and then you do homogeneous subset test. Okay. So after you have done this Tukey, and then you proceed to do clustering. I say clustering. Maybe it's not the correct word, but if you see the table, you will know what I mean. So what is homogeneous subset? Is you list all the group by placing them in the subset. The group that the mean do not differ significantly between one another is placed in the same subset. Okay. In this case, you resort to another post hoc test. We can use REGW, Gabriel, and also Tukey. So Tukey can do two things. All right. For example, okay, now you from Anova, you have established that there is one, at least one group is significant in plant height. Okay, but you don't know which one. You want to identify. So this is a multiple comparison table. After you have done, let's say, post hoc, you do your ANOVA, and then you administer Tukey tests to these three groups. So what happens is Tukey will compare pairwise. Let's say for 0 ppm, it compares against 25. Okay. So just look at the significant. So first round, you take 0 ppm, you compare against 25. Significant or not? Is there any significant difference? Ada ke tak? 0 and 25. Is there significant difference? Let's say alpha is 0.05. Different or not between 0 and 25? Okay, nak tanya siapa last sekali. Wait, dah habis dah? Okay. Alright. So, this one, not significant difference, meaning what? Meaning you can cluster 0. What happened? Always like this. 0 and 25. One cluster. Sorry, because I'm using mouse. And then 50. 50 is standalone. Because 0 and 50 ppm is highly significant different. Less than 0.05. So if you take 25, you compare against 0, non-significant. Okay, that's why you have two of these ppm clustered together. 25 against 50, significant difference. Still, 50 is being clustered at another subset. If you take 50 ppm against, compare against 0 ppm, very significant. Against 25, very significant, means it's standalone. It's not the same group. It's not the same member as 0 and 25. Okay. And then you do this. This is the homogeneous subset. By Tukey, you can say that 0 and 25 ppm. Say one group altogether. They are not significant different. So subset number 1, but 50 ppm treatment is different from this subset by using Tukey HSD. But if you use Duncan, Duncan is another type of post hoc test. Is used for small numbers of sample, small numbers of treatment. It's more stringent. So if you use Duncan, their separation is more stringent. So you may get different subset. Different subset for every concentration of gibberellin. So depending on what type of post hoc you use, maybe you get different result. Okay, for that, I finish the lectures on post hoc. Okay, which post hoc test to use? So you can read. So this is the criteria of choosing which post hoc. So equal sample size, variant. You can use this. Unequal sample size but variant equal, you may use this. This is all in the SPSS. You just have to know. Unequal variances, this is the post hoc that people will use. All right. So I've stopped sharing for today. Okay, see you next Monday. Tak cuti kan?